So now we want to consider two connected graph and two edge connected graph. We want to find some operations that, possibly help us to understand the structure of two connected and two edge connected graph. And for that, let's give a name to the following operation. In a graph G, we say a subdivision of one edge UV. If you have a graph in here UV, what you want to do is you replace an edge with a path of length 2. This is the operation of replacing UV with a path UWV through a new vertex W. So, in fact, this is to remark. This is the special type of vertex 2 split. If degree of U and degree of V is at least 2, both of them are at least 2, then so this was your original picture, and now this is the picture. So that means this subdivision operation preserves two connectedness. So if the original graph is two connected, then if you subdivide an edge, then its subdivision is also two connected. Moreover, this operation also preserves the two edge connectedness. This edge subdivision preserves two edge connectedness. So once you have a two edge connected graph and then you subdivide the edge, then the result is also two edge connected. Let's prove this. Let G be a two edge connected graph. And let H be obtained from G by adding W to subdivide the edge UV. And what do we know? So in order to prove two edge connectedness, we have to show that there are no co-edges. And we know that an edge is a co-edge if it doesn't belong to any cycle, and it is not co-edge if it belongs to a cycle. Such co-edges are the edges in no cycle. Every edge in G lies in a cycle. And edge, the same edge in H is also in a cycle in the corresponding cycle using test UWB if it uses UB. In G, on H is in cycle, and then that is happen to use the HUB. And in H, the same cycle, now instead of UB, you use the path UWB, then it's also in cycle. So this shows that every H in H is not a codex. Also, moreover, we have to check one more thing. No edges are codex, and then the graph has to be connected in order to be connected. But that's okay because replacing H and HUB with UWB shows that H is connected. So it is connected having no codex. So H connectivity of H is at least 2, so it is 2H connected. Okay, now we collected this operation. And before proving some operations that creates all two connected graphs, that was our purpose. Before doing that, let's justify what we are doing. So first, we justify studying connected graph because if we understand connected graph, we understand all graph. Because all not connected graph are disjoint union of connected graph. So now we want to say similar thing. We want to be able to say that if we understand two connected graph, then that will provide the understanding on all connected graph. In order for this, we need to define something like component. We want 2 connected analog of component. So for the connectivity, so every graph is disjoint union of component. So we understand component and we understand the graph. Similarly, we want to like two connected components. And we want to be able to say that if we understand those, then we understand every connected graph. For this, we define this analog of analog of component, which is a block of a graph is maximal connected subgraph of G that has no cut vertex. So for components, we define it to be maximal connected subgraph. But for block, we didn't define it as a maximal 2H connected subgraph. We instead want to define as maximal connected subgraph that has no codex, no cut vertex. That is subtle difference, and this will be more useful for us. Then what's a block? Which is with this definition, if your block has more than 2 vertices, it has at least 3 vertices. and it's automatically two connected. You have a connected graph which has no curve vertex, then if it has more than two vertex, then it is two connected. So it is maximally two connected subgraph as we wanted. But it's different if it has almost two vertices. It's either one vertex, two vertex, or maximal two connected subgraph. So blocks are either a vertex or an edge or maximally two connected subgraph. And moreover, these vertex and edge have a specific structure, meaning that, okay, if we have an edge, if it belongs to a cycle, then it is not a block, because what? It is maximal quantity subgraph that has no cut vertex, right? If an edge is here, there is cycle containing it, and this cycle, then this edge is not maximal connected subgraph that has no cut vertex, because this cycle already contains it, and it has no cut vertex. So it is not a block. So it is block only if there are no cycles containing this edge. So an edge is a block if and only if it is a cut edge. A vertex is never a block unless it is an isolated vertex. If you have a vertex, then there is an edge attached to it, then you might as well take this edge, which contains this vertex, and then is connected and has no cut vertex. The vertex is only block only when it is isolated vertex. So blocks are what? Isolated vertices or cut edges, and maximally two connected subgraph. Okay, so those three types of blocks are there, and then how they are interplaying. We already know how they are interplaying each other. How do we know it? So we know that an observation is that the two blocks share at most one vertex. If you have two blocks and then they share two vertices, then you take the union. And union is a larger block. It belongs to a larger block. So we know this. Two blocks share almost one vertex. Then what does it mean? What does it imply? Every block, they share only one vertex. So block partition edge. All edges belong to one block, and then it belongs to only one block. Any edge belongs to exactly one block. There are no cases that one edge belongs to multiple blocks. And also, a vertex shared by two blocks are cut vertices. If you have a vertex which belong to block here, and once you delete it, it should separate the graph. Sorry, my Siri the center. Anyway, so because what? If you delete this and then this does not separate it, and that means there is path between this and this. That provides a cycle here. Then you take this and then you take this and then you take this cycle, then that is two connected subgraph containing this block, contradicting the maximality of block. So that provides the following the block graph, which provides the understanding on the structure of the graph. How we consider set, say A, of all hot vertices and A of blocks. And we add H between say A and B if each hot vertex belong to the B, or each hot vertex and then block. Then what? Then this is a bipartite graph. It's called block graph of the original graph G. Then what you see is that this block graph is a forest. It does not contain a cycle. Because if you have a cycle, that means you have a block here, hot vertex, block here, hot vertex, and then they wrap up to find the cycle. Then you find this cycle, and that means that this one vertex is no longer a hot vertex. Even if you delete it, you can still connect this part and this part through this path. So this is a forest. Then this block graph gives the understanding that the G looks like you have block and then like hot vertex, hot vertex, hot vertex, hot vertex, and hot vertex, hot vertex, and block. And some of them could be, say, okay, maybe let's draw this. Some of them could be just an edge. So it is 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8. So this provides that the G looks this way. And this is what? You have a bunch of blocks, and then they are concatenated in tree-like manner or forest-like manner. Blocks concatenated in a forest-like manner. So if we understand block, then this block graph, together with this block graph, you understand the structure of G. Because we already understand the structure of trees or forest. And then in order to understand blocks, you have to understand what? So blocks are these three cases. Isolated vertices, codex, which we relatively, well understand this. We understand this very well. So we only have to understand maximally two connect subgraphs, which are, so we only have to understand the structure of two connected sets. Okay, that gives us the motivation for studying the two connected graph. And now we consider the operation that we wanted to discuss. that generates two connected graphs. So we define an ear on graph G is a path whose endpoints are in G and whose internal vertices are not in G, meaning that you have a graph G, and if you take one vertex, and add a path between them, then that's an ear. It could be simply an edge. In that case, there are no internal vertices. So, I mean, it's just an edge between these two. Maybe, yeah, I will add between these two. Or it could be a path with a new vertex outside of G. And we define on ear decomposition of G is a decomposition Q0, Q1, to Qk. Such that here decomposition means that the edges of these partitions edges of G. So edges of G partition into edges of Q1, edges of Q2, and so on. Such that what? Q0 is a cycle and Qi is on ear on the previous union of the previous graph for all I less 1. And we define one more concept of closed ear on a graph G is a cycle that there's one vertex with G. So it's the case where the two endpoints are the same one. So instead of that, you take one vertex and then you add a cycle. And this is a closed ear. And we say a weak ear decomposition of G is a decomposition Q0 to Qk such that Q0 is a cycle and Y is either on ear or closed ear on the previous one. So this provides some good understanding on the structure of two connected graphs. In fact, the following theorem fits me says that the graph is two connected if and only if it has an ER decomposition. And also, multigraph is threads connected. If and only if it has a weak ER decomposition. And we will prove the first statement only. The second one is, almost similar. Proof will work. Let's prove this way. We say that ER decomposition. Then what? We know that cycles are two connected. So your ER decomposition starts with the cycle. So it is initially two connected. And then you add an year. But adding year is actually same with adding an X and subdividing. So you have these two vertex, and then you want to add, say, this path, and that's same as you just add an X and then subdivide 3 times. Right? So, but what we know that this preserves two connectedness. And subdividing it also preserves two connectedness. So your final graph must be two connected. So that direction is easy. I will not write down all the details. And for the other direction, suppose that G is two connected. Then what? We let H be say maximal subgraph which had an ER decomposition. Okay, then why H has to exist to begin with? Then this H is not empty, as G contains at least one cycle. It is two connected, so it has at least one cycle, and this cycle has an ER decomposition. So there must be a non-empty H, which is maximal subgraph, having an ER decomposition. So if H and G are same, then we are done. If not, then we select H will be which is outside of H, but in G. You have H and you have UV same. Sorry, the other way, that's it. And moreover, that's that the U is in H. So because G itself is connected, then out of all edges in G, not in H, you could choose the one which connects the vertices of H and the outside. Such an edge exists as G is connected. Okay. And what we know, just is two connected. But there exists path P in G minus U. So you delete this, there must be a path P which is from B to vertex of H. Then what? P together with the H, UV is an ear that can be added to H, contradiction to the definition of H being maximal graph with a near decomposition. As H must be G, so G has an near decomposition. So this proves the theorem. And for the second one, I mean, this direction is still okay. And for this direction, you just replace it with the G minus UB. You just delete the H and you find the P, which possibly give you a closed ear. So that the second weak ear decomposition statement is also true. Okay, so we prove this theorem. So this ear decomposition actually helps us to understand the structure of two connected graphs and two edge connected graphs. Maybe as an example, I mean, let's consider one problem which can be solved easily using this concept of ear decomposition. So, similar with the connectivity, and we can define the similar concept for the digraph. For directed graph, I mean, connectivity here has to be, I mean, so what's connectivity? For any two vertex, we can find the path between them, right? And in digraph, we ought to find the constantly oriented path. So not just any path, but the paths that allows to move transport one to the other. So we want this kind of path, not like this. This is not good, this is good. I mean, in many cases, you can come up with the problems which is related to this concept. For example, I mean, if we have a city and then you want to move from one place to the other, and all the streets are one way, then, I mean, if from here to here you cannot go because these streets are one way. In that case, not just connectivity is enough, but we want to come up with a stronger definition. And we say that this is strongly connected, or simply strong, if for any U and V, there is this directed path. Usually in diagram, if we just say path, this is directed path from U to V. And what Robbins in 1939 proved is that if you have a multigraph, and when can we give an orientation so that it becomes strongly connected? So it has a strong orientation. We can give orientation on each edge so that it becomes a strongly connected graph. If and only if it is two edge connected. And proving this, I mean, one direction is easy. What? This direction. If we have a cut edge, so what's the contrapositive of this? Meaning that if we and not two edge connected, then it doesn't have a strong orientation. If you have codec, then what happens? You have codec, meaning that this part and this part are disconnected after using it. But if we orient it this way, there is no way to get from here to there. So it is not possible. The only possible road to leave the component is this one, but it's not oriented as we want. So if there is a codec, one cannot travel both ways. Across the edge code. So this direction is easy. The other direction, we use weak gear decomposition. You have a two-edge connected graph, so we have a weak gear decomposition. Then what we do, we orient the initial cycle consistently to obtain a strongly connected diagram. Your cycle is consistently oriented, and wherever you start, you just follow the orientation, then you can visit every vertex. So this is a strong diagram. And every time you add a new year or new cross year, you orient each new year or cross year Q from one end U to the other P. So whenever you add a new year, you arbitrarily orient from U to P in a consistent way. It could be U to U, from U to B is okay, from B to U is okay. Then what? Sensitivity implies that the new diagram is strong, right? All the vertices, and from all the vertices we can reach U, and from U you can reach all new vertices. And new vertices can reach B, so wherever you start you can reach B, and B can reach all the vertices. And between here to here, say you go here and then you go here, you go here. So, I mean, using transitivity of reaching, you can reach every old vertex can reach new vertex, every new vertex can reach old vertex. Between all the vertices, it's already established that you can reach it. Between two new vertex, you take a new vertex to old vertex and old vertex to new vertex. So you keep doing this, and after all years, cross years are added, we have a strong orientation object. So this proves what we want. Okay, so we learned about the gear decomposition and two weak gear decomposition, which help us to understand the structure of two connected graph and two edge connected graph. And in the next video, next time we will study about the three connected graph. Thank you for listening. See you next time.